It also at some point stopped recording.
Uh-oh.
Oh,
So
Oh, we did not
we
start
didn't
the-
start it again after we talked
started
earlier. That's okay. We haven't done
okay,
too
it's
much.
not too.
Yeah.
You
Is it
guys
any
did
better?
not record? Oh,
Yeah, we didn't record it.
that's okay. Venkat, can you see?
No,
I don't
I
think so,
can-
yeah.
For some,
Huh?
it looks fine on here. It looks weird on there.
Oh, I see.
This screen, like, you can verify that, like, this screen looks fine. This
Do you
looks.
think? Well, look at the bottom. See, I don't think you're cast. Look at the.
Oh,
Yeah,
yeah,
like,
the
all
jazz
the
yeah,
is weird.
Yeah, so the TV is not
Really?
good.
No, but this is, they are also seeing this.
They are also having problems. So let's go to the other board then. Let's try that. If that helps.
I'm not sure if it is a board problem.
Then we go back to the old camera.
Let's go there.
Hopefully that's not the case. They spent a pretty penny on it. But oh, it doesn't work.
Did you start recording though?
Yes, it's recording. We double check that. Yes, it's recording.
Yeah, just ask for the host key from me
Mhm.
so that I can give you the host key, then anytime you can.
Gotcha. Yeah, for some reason Zoom likes to do that. Like when we recorded the quantum group, it actually just did that to my computer. Like it fried the screen like that for some reason.
Huh.
And then it didn't fix until after I restarted my computer. I was like, what is going on?
Is it messing with your like trying to mess with the graphics card maybe and
If it is, that would stink, but I'm. I didn't do it anyways. Being put in the language straight.
I have to surely write bigger, it seems like. Better?
Yeah, that's legible.
Yeah, it looks okay.
It's okay, not good, right?
Right.
Let's go to the center board, come on.
Oh, come on, charge it.
No, you know what it is, okay.
Shajes, can you divide that board into like half? If we can
Yeah.
use the right hand side, second half, maybe.
Yeah.
It'd be better.
I think the problem is that it's just so tilted out of frame.
You just gotta move the camera. It's supposed to be a mobile, no, it's supposed to be a mobile, right? That's the whole idea, right? This is, what does this say? What is the name of this?
well it's called near stream, so maybe it just doesn't like being far away.
I mean, this is for streaming, correct? They carry it with them.
Yeah.
It's, the idea is that, so we just try to make it,
It just doesn't like equations.
okay. So.
Maybe like optical filters that I have that you could play with maybe.
They
To
don't-
make it better on a board.
They don't, like, they don't need all the filters that it really has, especially for, like, the camera doesn't have much. Zoom, literally, all it can do is change your background. Like, no filters.
This is the,
Well, maybe does that have like a program that comes with it to access things?
Yes, sir.
Well,
But that's it.
that sounds crazy to me.
okay. So again, we were interested in limit delta tends to 0. Delta over omega squared. Plus delta squared. Let's start with let's say omega is equal to 0. What is it? If omega was equal to 0?
Delta.
And 1 over delta, and then you take the limit, that's infinity, right? And if omega was not equal to 0, that means it could be the tiniest amount of the 0, that as you take the limit, there will always be a situation where this is small. So this goes to 0. If it is not 0, then I can neglect that. So the numerator is going to 0, so that's equal to 0, right? And that seems to suggest that
That's 0 everywhere.
so this is 0 everywhere except omega equal to 0. So if you were product, it's something like this omega. So it's something like this. And you remember Dirac delta function has this feature, but it also has to have this feature that the sum of that integration should be one. Right, so let's do this integration also. Let me do integral of d omega delta over omega squared plus delta squared, again being free with taking the limit and integral and changing. Freely, liberally doing that. And this is reasonably easy to do. Substitute omega is equal to delta tangent theta, I guess. So then you would have when omega is plus infinity, theta is minus pi by 2, I guess. So this is plus pi by 2. This is minus pi by 2. And d omega is delta secant square theta, d theta. And the denominator I have delta square and then 1 plus tangent square theta. Reasonable? And these two cancel out. There is a, what am I missing here? Help me. There was, oh yeah, there was already a delta here. And then
Another
Delta squared,
yeah, delta squared. So notice that limit went away. So there was limit became independent of the limit. That's very sensitive. It happens only with very clear choices of numerator and denominator. So that's a very fine balancing that is happening. And this is equal to pi. Which means that I should divide out by pi. So this is actually equal to a delta function of pi. So going back, what's the frequency? If you have a step function, what is its Fourier transform? That will play a role when we are thinking of causality. Its real part is a delta function. A simple step function. What is its Fourier transform? Its real part is a delta function, and its imaginary part has still this feature, and we'll keep that as it is. Omega over omega squared plus delta squared. If I were to plot this real part, so this is a real part. This looks in very twisted manner. A delta function is something like this. So that's frequency. And imaginary part is here. This spreads out. So notice that is my this one, right? So imaginary part of omega, correct? So it is 1 over omega. So it goes away. So that's your 0. So I think it is something like this. I think so. And this is just the functional form of it. And that is a, like we will very soon talk about its breadth and all that. This is, in some sense, it will get connected. All your refractive index will have this structure. And absorption coefficient will have this structure. As I said later on, this will get into what we said Kramer-Stromick relation. But currently, it is just a mathematical structure. What is the Fourier transform of Heaviside step function? It's a delta function. It's in frequency, it contributes, the real part gets contribution only from one frequency. And the imaginary part has this structure in there. So we want to build intuition for it. Homework, like not really homework, we won't have homework in the strict sense, but what you can think of is, now we want to go back and do all that polarization part, right? So we want to talk about step function, how it looks like in the Fourier space. Next thing, what if the function is real? We will have electric field to be real, right? So if electric field is real, what about E of omega? How does that look like? Like a real function in Fourier space, how does that look like? That's one thing we want to know. Second will be if some function is odd, right? Why odd? Because this now has the step function feature and our susceptibility will have this, which means that on the left side and everything is zero. So I can choose whatever I want to, and I will use it an appropriate symmetry in there so that it becomes convenient. So I will use the odd function nature to that. So we want to ask if a function is odd, so in time space, if a function is odd, how will it look like in the frequency space? What does the oddness of a function in the time space look like in the frequency space? And then what? I guess this is and we said non-locality becomes local. The same thing, locality will become non-local in that. So this is what we will do next time. So I will stop and here. 2 minutes cross the heart, stop. Okay. Okay, thank you, Niranjan. Yeah, how was it? And the center board is reasonable, it seems like, right?
Yeah,
Yes.
center board is pretty clear.
Okay, this board is.
By pretty clear, you mean it is not blotchy at all, like it's like focused.
Yeah, it is focused like when you are in the middle board, center board.
So middle board is good, so we move around with the camera. Okay, thank you.
Yeah, thank you, Dr. Service.
Okay, everybody's going to leave. Okay, so thank you, Dr.
Bye.
Sajas, then, and I will see you guys next time.
Uh-huh.